Here's an example problem on electric circuits that was taken from an AP exam. This was taken from the Electricity and Magnetism version of the Level C AP exam from the year 2000. This is problem number 1, and it shows us 3 light bulbs connected in a network with a 42 volt EMF, or an idealized battery voltage. We need to list the bulbs in order of their brightness. Now when I hear brightness, I think power. Which bulb has the greatest power rating? From brightest to least. And if any bulbs happen to have the same amount of brightness or power, we'll have to state which ones. So instead of being given a wattage for these bulbs, we're told what's the resistance of their filament. Perfect. If we want, we can diagram this circuit another way. Let's just start out by drawing these as resistors instead of light bulbs. Maybe that makes it a little easier to relate to. Okay, so there's light bulb A. So there's these 2 points. We can call them points X and Y if we want. So I've got my point X and my point Y. Okay, well it looks like between points X and Y, I can either encounter the resistance of bulb B, or I can take a different path between X and Y that encounters the resistance of bulb C. So there's the resistance of B, and you might think I want to draw the resistance of C here, but for me it's a little easier to picture it as if it's here. After all, it doesn't matter so much where it's located along that path, just as long as I have the resistance on the correct path. So there we have it. Why don't I draw it like this? Let's rotate it and say we go from the positive terminal of the battery through a resistor, and then we reach a junction X. So we go from the positive terminal of a battery, and then we go through a resistor, and then we reach a junction X. Once we get to that junction X, we can have 2 possible paths to get to point Y. So from junction X, it splits off, and these 2 paths each have just 1 resistor on them. So one of them has resistor B, the other has resistor C, and those 2 recombine at some point Y, and then from there it's off to the negative terminal of the battery. I like that circuit diagram a little bit better than this one. It's easier for me to relate to anyway. And this is equivalent to, well, let's plug in the values now. This is bulb A, these are bulbs B and C, and so A was given as 10 ohms of resistance, and B was given as 12 ohms, C was given as 6 ohms. Well, B and C are clearly connected in parallel, and the rule for parallel says the equivalent resistance is the product over the sum. So this is 6 times 12 divided by 6 plus 12, or in other words, this is 72 over 18. 72 over 18, those are both divisible by 9, aren't they? So this is 8 over 2, oh, that's 4. I should have seen that. The equivalent resistance is equal to 4 ohms. So this is the same as a circuit with a 42 volt EMF, and then we just have 10 ohms in series with 4 ohms, so it might as well be just having a single 14 ohm resistor. And by Ohm's law, current is voltage over resistance, so if I want to use the full battery voltage, I have to use the overall equivalent resistance of the whole circuit. If we divide 42 volts by 14 ohms, then we get a value of 3 amps. Whew. We still haven't answered the question. We need to list the bulbs in order of their brightness. Okay, so go back to our original circuit about here, and we just found the amount of current flowing through the battery is 3 amps, and that then is the amount of current through our 10 ohm resistor. Power is current squared times resistance, so this is going to be 3 squared times 10, which gives us 90 watts. So we've got a 90 watt power rating for resistor A. Now, that 3 amps is going to split up. Okay, resistor B is 12 ohms and resistor C is 6 ohms. So whatever the current is through resistor B, I'll just call that X. Yeah, okay. I don't like that I labeled a junction as X and a current as X, but you're with me on this one. If the current through resistor B is X, then the current through resistor C better be 2X. With half the resistance, you're going to get twice the current. So by applying Kirchhoff's junction rule to junction X, 3 amps flows in, and then that has to equal X and 2X flowing out. Oh, 3 equals 3. So X is equal to 1 amp, meaning 1 amp flows through the 6 ohm resistor, and, oh, I'm sorry, X is equal to 1 amp. So I've got that backwards. 1 amp flows through the 12 ohm resistor, and 2 amps flows through the 6 ohm resistor. Well, that adds up, right? If you have 1 amp flowing here and 2 amps flowing here, that's the way in which the 3 amps is splitting up. So some nice round numbers were chosen for this problem, it seems. All right, so power is current squared times resistance. So we already found the power for bulb A. Let's find it for bulb B. The current is 1 amp. We square that. We multiply it by a resistance of 12 ohms. Oh, so we get 12 watts. Clearly not going to be as bright as bulb A. What about bulb C? Power is current squared times resistance. Here we've got a current of 2 amps. We square that. We multiply it by a resistance of 6 ohms. 2 squared gives us 4, and 4 times 6 gives us 24 watts. So if we want to list them from brightest to least bright, then it goes A is brighter than C, which in turn is brighter than B. I think we've got it. The problem doesn't end there. Now we're told that the circuit changes a little bit and an inductor is added on the branch along with the 6 ohm resistor. That inductor has a value of 5 millihenries, and at time t equals 0, this switch is thrown into the closed position. Now we have to find the currents in bulbs A, B, and C in the following 2 cases. 1, immediately after the switch is closed. 2, after a really long amount of time. Okay, so let's do it for immediately after the switch is closed. Well, immediately after the switch is closed, initially, since the switch is open, the current is 0. And then if you close the switch, a current has to develop in accordance with the polarity of our battery. And so even though the current is at its minimum value of 0, the rate of change of current initially is at its maximum value. And when the rate of change of current is maximum, then the resistance of the inductor might as well be infinite. So no current flows through light bulb C immediately after the switch is thrown. And so current just flows through this upper loop that has 10 ohms of resistance in series with 12 ohms of resistance. So to answer this first question, what's the current immediately after the switch is closed? Well, Ohm's law says I equals V over R, and so 42 volts is applied to a path of 22 ohms. 42 over 22, we can call that 21/11ths of an amp and leave it at that, or we can express it as a decimal. 21/11ths gives us 1.91 amps. Now, that's the current in bulb A and in bulb B, so let's make sure we're answering the question that they've asked carefully. IA is equal to 1.91 amps. IB is equal to 1.91 amps, and IC is 0. Now, after a very long time, what are the currents? Well, after a really long time, the inductor might as well just be bare wire. It offers no resistance. After a really long amount of time, the current's grown to whatever value it's going to be, then at that point, di dt is equal to 0, and the inductor offers no resistance, and now the circuit is just right back to what it was previously. The inductor might as well just be a segment of bare wire, and so we've already found those values. The current in A is equal to 3 amps. The current in B is equal to 1 amp, right? And the current in C is equal to 2 amps. Okay, not bad. On the axes, sketch the magnitude of the potential difference across the inductor as a function of time, starting from the moment it's first closed until a long time after. So initially, the potential difference across the inductor, let's see, the potential difference across the inductor, that's the potential difference from here to here. Okay, well, if no current is flowing initially through bulb C, then the electric potential at this point is the same as the electric potential here. So I think what they're really asking is, what's the potential difference across light bulb B? And then after, and then after a long time, what's the potential well, after a long time, the potential difference across the inductor has to be 0. We know that for sure, right? If it offers no resistance, then there can't be any voltage. After all, voltage is current times resistance. So in the steady state, as t approaches infinity, if at that point the effective resistance of the inductor is 0, then any amount of current that flows doesn't matter. If the resistance is 0, the potential difference is 0. So we know this axis is going to represent an asymptote. We just need to figure out what the initial value is. So like we said, the initial value of the potential difference across the inductor is the same as the initial value of potential difference across light bulb B. Well, the potential difference across bulb B is the current through bulb B times the resistance of bulb B, which is 1 amp multiplied by 12 ohms, which is 12 volts. There we have it. Now we need to consider a different case. This time, a capacitor, instead of an inductor, is placed at that part of the circuit. And then the same situation here. We need to sketch the magnitude of the potential difference across the capacitor as a function of time, starting from the moment the switch is first closed until we reach a long time later of the steady state. Okay, so initially, the capacitor offers 0 resistance. So this is the case where the initial condition is 3 amps flowing through the 10 ohm, and then it junctions off 1 amp through the 12 ohms, and 2 amps through both the 5 microfarad capacitor and through bulb C. Okay, so let's find the electric potential at all these different points. Let's imagine that this part of the circuit is grounded, so the potential right here is 0 volts. Let me switch the color of my pencil. The electric potential right here must be 42 volts. When 3 amps flows through 10 ohms, you lose 30 volts. So we go from 42 volts minus 30 would get us down to 12 volts. Okay, and when 1 amp flows through 12 ohms, you lose 12 volts. So thank goodness that agrees. That means our potential difference is back down to 0 volts right here. So let's see, the electric potential here is still 12 volt. The electric potential here is 0. Let's see if we can figure out what it is right here. Well, 2 amps is flowing through 6 ohms of resistance. So that gives us a potential difference of 12 volts. So, the electric potential here is 12 volts initially. So initially, what's the potential difference across the... It's 12 compared to 12. It's 0. And of course it's 0. Initially, the resistance of the capacitor is effectively equal to 0. And if it acts like a circuit element with 0 resistance, then it has to have 0 potential difference across it. So, at time t equals 0, our potential difference is 0. Okay, so this isn't a graph like the previous one that starts out with an initial value and decays to 0. This is going to be a graph that starts out at 0 and asymptotically approaches a maximum value. Let's see if we can figure out what that maximum value is equal to. So we've got some erasing to do here. Now let's consider what happens in the steady state. At that point, the effective resistance of the capacitor is infinite, and so no current flows on this path. Well, if that's the case, we've already figured this out. That means the current that's flowing here is 42 volts divided by 22 ohms, and that gave us a value of 1.91 amps. Okay, so 1.91 amps is flowing through 10 ohms of resistance. So if I multiply that together, I get a voltage drop of 19.1 volts. So if the electric potential here is 0, and the electric potential here is 42 volts, let's change colors, 0 and 42, then the electric potential right here is 42 minus 19.1. So 42 minus 19.1 gives us 22.9 volts of potential difference. The switch has been closed a long time, so this 0 volts is also the potential here. Okay, so if no current is flowing through the 6 ohm resistor, then the potential here is also 0 volts. So the potential difference across the capacitor is a difference of 22.9 volts compared to 0 volts. 22.9 volts, and there's the graph. So just another good review problem, not only in RL circuits but also in RC circuits. There's an RC circuit, there's an RL circuit, and here's just a combination circuit of resistors.